Log on, tune in, find out. Another good idea from Cambridge.
From Manchester.
Okay, thank you very much. Thank you for coming, and I hope, so I feel like I'm the entertaining after tea break talk, hopefully. And I'm going to talk about an offset cone beam tomography system, but actually the thing that's slightly different in this talk is it's an application for airport security rather than medical or geophysics or things that we've seen before. And I'm hoping to tell you a bit of a story about this. So a brief outline, I'm going to talk about X-ray CT for airport security, and I'm going to talk in particular about the way that we solved it using a multi-surface rebinning reconstruction algorithm. Although I'm going to hide quite a lot of the technicalities. There is a conference paper and a paper in preparation that you can get the details. And I guess the details are probably only going to be really of interest if you want to do something similar for your problem. But so the bones of that. I'm also going to talk about the firing order and some algebraic methods we used. Very briefly, I'm going to say why the solution is unique but unstable. And I'm also going to talk a little bit about scattering modelling. And all that, and still finish in time for questions, unlike the previous two speakers. So it's been suggested that if I do that, then I can take questions on the previous two talks, but I'm not sure I can do that. Okay, so airport baggage screening. So, this is actually, everybody wants to do this better, actually. So, not just because we want to travel more safely, but actually if you do this better, you can also do it more cheaply and more quickly, both of which is in the interest of the airline, the airport, and us as air travellers, right? Because we don't want delays and we want cheaper flights. So it's all good to improve airport baggage screening. So hold luggage has to be checked for bombs. You don't really mind knives, guns, stuff like that. They're leaving the country anyway. But you're looking for explosives and a detonator and an actuator. You're looking for bombs. This is the hold luggage. The cabin luggage, of course, you have to detect lots of other things. Okay, so mostly, in most airports, bags are X-rayed with just a transmission radiograph, as Simon set me up very well, because he had some of those at the beginning of his talk. And an operator looks at the picture and decides whether it's a bomb. Actually, I've seen people do this, and they're incredibly skilled operators. And we looked at some mystery objects, and we thought, well, that's got a big lump of something, and some wires could be a bomb. They said, no, that is a folding travel iron from unfamiliar angle. So, these people are highly skilled at recognizing things. There are many technical problems. If your terrorists are ingenious, explosives can be, for example, made into very thin sheets or concealed by denser objects, which is why, for example, you have to take your laptop out of the bag. But viewing it from one direction just might not do the trick. So three-dimensional images allow the operator to identify objects better and improve automatic screening as well. So typically, 3D baggage screening systems render it as a translucent view that you can then rotate round and you can say what's under there. Okay, so some airports, such as Manchester Airport, have a hospital-style X-ray CT scanner. So it's a big clunky thing with a rotating gantry, just as you see in a hospital. These are slow and they're very expensive. And so typically where they're used is a second level of screening. Once you've seen on the transmission, on the radiograph, something that could be explosives, its density, its size, it could be a Christmas pudding. But after that first automatic screening, it's sent to a CT and that's looked at by the experts with usually one carefully chosen slice. So Rapiscan developed a very fast X-ray CT machine, and the idea was you just put all the bags to a CT machine, and it was fast enough to do that. The bags go through about 0.5 meter per second on the conveyor belt, and that's much faster than a typical hospital. But to achieve that speed, the geometry was different. That's a sort of GE hospital-style CT machine. Actually, it's got a conventional X-ray radiograph machine there, and then a CT. And this is the Rapiscan RTT80, of which there are production prototypes at the moment. But I'll tell you a story later. There's a picture of a bag on the screen. It does work. But so why is it so different? Click for animation. I think Alt-Tab will probably do, as long as it's not broken. Escape, Alt-Tab, and slideshow should do it. Abracadabra. There we go. Right. I couldn't get this in the PDF. So this is a conventional CT machine. It's got an X-ray source and, say, for example, a curved array of detectors. And this has several rows of detectors, so it's doing a 3D cone beam scan. And the whole apparatus rotates around. It's very heavy, and so there's a limit to how fast you can make it go round. This one, however, has a ring of X-ray sources that are fixed, and so they switch on and off. And then the detector array is at a different radius, and actually it's offset. It's behind the picture if this is in the picture plane, because you can't have detectors in the same place as sources, right? Because they have to fire through them. So this creates a very different geometry, but of course there's no mechanical rotating components, so it's going very, very fast. Actually, you don't even need to switch it in order. I mean, this would just be to make it look like this. You could switch every 30th one or something like that, or switch them in a random order. There's no limitation to that. They're just switched on and off. In fact, actually, that's almost the hardest, because switching on sequentially creates more problems with dissipating heat, so you probably don't even want to do that. Okay. But I have to go to full screening. Okay, so here's a little story. So it's a bit of a case study in doing maths with industry in a way, because some of these features are quite common. One feature that's unusual about this problem is going from first starting it to actually doing something useful in a relatively short time. Actually, I claim that, but we rely in part of this on the work of Fritz John in 1938. I had to get Duke Math Journal 1938 from the library storage to look at it, but it's very relevant to 3D X-ray CT. So some theory has a very long time before it becomes useful. But in around 2006, Rapiscan, and specifically the guy who invented this real-time tomography, RTT, Ed Morton, approached us and said, well, we don't know. We don't know if this is a solved problem or if it's completely new research, and asked us to have a look at it. So to spend 3 days looking at it. And actually I was a bit dismissive. I teach 2D X-ray CT to undergraduates. I thought, how hard can it be? And it's linear, you know. I was used to working on non-linear inverse problems. But it turned out that with this geometry, with the sources offset from the detectors, there was really nothing done on this before. So this got me excited, and so I applied for a grant, which was a Maths and Industry and Business grant, with matching funds from Rapiscan, with the intention of looking at this. And one of the kind of morals of doing industrial maths is that you have to give them something, actually, quite early on. Because usually by the time they ask you, they've already promised to do something and they don't know the mathematics. By the time they ask mathematicians. And this was the case indeed. So we implemented something fairly crude in the meantime while we were waiting to get a grant. We got the grant. I recruited the team. Actually, none of us had worked on CT before. Inverse problems, yes. Numerical analysis, yes. But we were beginners at CT. And actually, Rapiscan kind of liked that, because we weren't going to just turn out the same old solutions. But actually, that was perhaps rather ambitious, to learn CT, implement it, solve the problem. And the things that we looked at, in particular, we needed a reconstruction algorithm. We needed one that was fast enough to work in real time on hardware that was feasible. We were also worried about the scatter correction. Let me just explain that because the detectors are fixed, they're facing every way, they have to be able to receive X-rays from every source that's incident on them. A normal hospital CT would have collimators so that it would only get photons looking in the direction towards the source. And so this system is potentially vulnerable from scattered photons, and we were interested to model that and maybe correct it. And then the other thing is the firing order, sequential isn't necessary on this, and so what would be the best one? So we did most of this. We managed some reconstruction algorithms that we implemented and tested on real data and patented before we published them. And they're in process of the technology translation of being implemented on the actual prototype system. And so that's the stage that we don't do. I mean, it's down to professional software engineers to do that. Our scatter model was successful, and in fact, Nicola Wadeson, who developed that, was then seconded to Rapiscan to work on another kind of security application that involved the same simulation. And also we implemented this firing order that's tested on simulated data, and actually has been tested on the prototype to some extent as well. Okay, so Simon again has set me up because he's told you about X-ray transform, as though you didn't know, but let me just reiterate a little bit. The X-ray transform on a function in R3 is the integral along a line. So you get a point X in the direction xi, and you integrate along that line. Okay, so there are an explicit inversion algorithm if you knew all the points. More generally, though, there's a four-dimensional set of lines in space, and you only want a function of three variables. So usually you choose some three-dimensional subset of lines. And ones that work are all the lines in parallel planes, because you can do that slice by slice, or in particular, all the lines that go through a helix. And that's the usual case in a hospital CT scanner, because the person's moving along as the source goes around. It describes a helix. I'd just like to say one other thing that's known. The Radon plane transform is the integral over planes in R3. It's the analogous thing of Radon transform in 2D, and that's useful to analyze the X-ray transform when you've got a whole plane of lines. So that will come into the story a little bit later. So actually, just to skip over this briefly, for a helical scan, there are explicit reconstruction algorithms, but they need enough of the rays. So the detector that you saw in that picture has to be wide enough rows relative to the pitch of the helix. So there are explicit analytic reconstruction algorithms. Actually, let me show you a picture rather than just words. This is a cartoon of the RTT system. There is a bag, there's a conveyor belt, and I want you to think these are sources that are switched on and off, and each of these little squares is a detector. So we're measuring, so these are both circular out of the plane, and the rays that we measure go from these sources to these detectors through the bag. The scale is exaggerated. It's, of course, actually as narrow as we can make it in that way. So a conventional helical scan system, the source would go around the helix relative to usually the patient, and then you'd have an array of detectors that's wide enough according to some rule, and you'd measure all the rays which are both above and below the horizontal plane in this picture. Whereas, and again exaggerated, if the detector's offset from the source, then you're only measuring rays at an angle, because this is an exaggerated cartoon. So how do we do this reconstruction? Well, let me just introduce a concept that's important, and I'm not actually going to write down all the equations, because actually the notation's a little bit heavy to get to grips with. But here's our XYZ coordinate, and there's a source going around here. We think of a plane through the z-axis that's a virtual detector plane. Actually, your detectors are further away, but it's convenient to work in the plane of the axis. And on that plane, the rays that we measure are between these upper and lower bounds. In a conventional system, it would look more like this. And so this truncated data is our problem here. Okay. So that's a truncated kind of window of measurements that we make. So this, actually, as you see, it's the U and V coordinates are usually the coordinates on the detector plane. Okay, so I need to introduce the concept of rebinning. So one method of reconstruction for a helical scan system is to use the 2D reconstruction, because there's an explicit inversion formula for 2D radon transform. But of course, we haven't measured all the rays in all planes. Well, usually we've measured all the rays in one plane. What we do is make a surface that's tilted at the same angle of the pitch of the detector, and we don't know all the rays on that surface, but we interpolate them using the rays that we know. And that's called rebinning. And so the point is, once you have all the rays on a plane, then you can use 2D radon transform. There's a method called surface rebinning, where you make a slightly curved surface that the rays are on average closer to, so the interpolation works better. Again, the scale in Z is exaggerated here. And there's a specific iterative algorithm that converges to this optimal surface that's closest to as many rays as possible. But in the case of the normal geometry, it's very close to being flat anyway. As soon as you truncate the detector, it becomes quite markedly curved. What we found, though, because we only measure rays pointing upwards, not upwards and downwards, rays tend to be only close to this surface for half of it. So the idea which Marta Betke had was to find a two-sheet surface that's close to the rays, and it turns out a typical ray is closer to the top half for part of its trajectory and the bottom half for the other part of its trajectory. And so we had a very cunning idea, which is illustrated in this picture. So this is these are the sources firing, and in this case it's a triple helix. It doesn't really matter. And the idea is we'd measure on rays like this and like this. But if you take that V-shape there, the green and the purple, and that purple and green, then what we've got is the integral over this V and this V added together. So if we project this onto the xy plane, what we've got is not the integral over lines, but the sum of the integral over that V shape and that V shape. We can do the 2D reconstruction of that, and that doesn't give us the answer. It gives us a reconstruction of the projection of the sum of these two. We're left with one problem: to solve a pair of simultaneous equations to separate out these two sheets. Fortunately, each point goes through both sheets, apart from that singularity there. And so we have simultaneous equations which couple the two sheets together, so we have a very sparse system to solve. So the reconstruction algorithm involves essentially 2D reconstruction, which they'd already implemented in hardware in a very quick and efficient way, plus a sparse regularized system to separate the reconstruction on two sheets. And so that was our idea, and well, it works. I don't know why we got into the mood of scanning musical instruments. I think partly the guys testing it were just messing about. But anyway, here's a guitar, and we have a complete 3D rendering of this. And it works that there are some artifacts associated with the metal. And actually, we chose the colouring to show them. I mean, you can turn it down and not see them, but we wanted to show you the worst case of that. So this is a complete 3D rendering. We've just looked at a semi-translucent view of it to make it look pretty for you. Okay, so that's actually with the RTT-80 machine. So I'm going to say a little bit about firing order, because I mentioned that the sequential order, which emulates the standard rotating hospital CT system, isn't necessarily most sensible. And so we were looking at criteria for which would be a good source firing order. And there's at least two different ways to look at this. I mean, when we were thinking a multi-threaded helix might be good. In fact, typically they use something like a 3-threaded helix naturally anyway. They thought that was a good idea. So one way to look at it is the density of rays hitting each pixel, which ought to be uniform if it was good. And the sequential firing order has a very non-uniform density of rays hitting each pixel. The pattern currently used by the RTT, I guess it probably is 4-threaded helix, is that one. And the optimal spacing, where you skip 35, so you fire every 35th one, and that actually maps out all of them, is very uniform. So that looks winning. And there's another criteria that you could use, which is, and we couldn't do this for the full resolution system, we had to use smaller pixelization. You can look at the matrix and estimate the condition number. So somehow the best firing order should, obviously the matrix will be ill conditioned, but a better conditioned matrix is good. And it turns out we get the same answer. So the skip 35 firing order looks good from that as well. Since we assembled it as a matrix, we also looked at algebraic reconstruction. In other words, take Chris Farmer's advice here, it's just a system of equations. So what you'd want to do is write down the equations, write down your prior, and find a regularized solution. Now in X-ray CT, they often use some very hokey linear algebra iterative routines like Landweber and Kalkmarts and things like that. They use these because they're slowly converging, and they stop them and call that regularization. But it's completely unsystematic regularization. I mean, okay, so there might be a null space we could hide a bomb in, but we'd like to know what the null space is. We'd like to know what the assumptions are in our algorithm. So we prefer to use conjugate gradient least squares, and if we want to, we can augment that with a regularization term, and then it will converge very quickly. And that's very efficient. In fact, we've implemented this in a GPU, so it can go fast. It can go not quite as fast as real-time baggage scanning requires yet, but it's on its way. This is simulated data from an array of cuboids, and we added 5% random noise just to mess it up, and put the contrast up so you can see it going wrong. But this illustrates the converged solution with the sequential order, the one they're using at the moment, and our optimal one, which is reasonably convincing that that's a good firing strategy. Okay, so I wanted to put a different way of looking at this. It's conventional to think of a CT scanner as modelled by a continuous curve of sources. Of course, everything's discrete. I mean, you take discrete measurements at certain time intervals. But in our case, it really is discrete. We fire these sources, and they're actually separate sources. And we're conventionally thinking of them as a helix or a double-threaded helix. But it occurred to us that once we choose our optimal kind of spacing, and so this is a polygonal cylinder. It's polygonal because that's the way the system's actually made. And this could be a helix or multi-threaded helix, but in the end, you're just sampling a cylinder. So is this lots of helices tightly wound, or is it just samples on the cylinder? Well, actually, the best source spacing would be to sample a nice regular grid on the cylinder. This is a completely different way of thinking about it. You see, so the point is, we can fire in any order we like. We'd like to fire in an order that covers a cylinder well, rather than draws a line. And in this case, we're actually sampling a 4-dimensional data set. Or, let's put it this way. When you look at an inverse problem, and you look at the continuum version with infinite amounts of data, not discretized, then you prove uniqueness of solution for that. This is an idealization, and usually you're interested in non-uniqueness, right? That has more impact on the subject. However much data you measure, you still couldn't get the answer. But it's reassuring if you say something that you're approximating that has a unique solution. And so in this case, we're measuring a limited 4D set of data in this idealization. So let's just analyze that very briefly. So the idea is that we measure all the rays that are in some range of angles to the z-axis, because we only measure rays with a certain tilt to them, to the axis, because of our offset. We can't measure these rays. We can measure those ones up to there. So we have a range of tilts that we can measure, and within that we can actually measure a full set of rays in a plane. In other words, we can measure an integral over a plane if we wanted, by using enough rays, which gives us the radon plane transform. Now, if you take the Fourier transform of the radon plane transform with respect to the s, that's the distance that the plane is from the origin, you Fourier transform that, then the Fourier slice theorem says that that's the Fourier transform with sigma multiplying the direction vector of the plane, obviously the normal vector to the plane in the Fourier space. So if we say measure an interval of sigma and a cone of xi, that's an open set of planes. And if F has got compact support, which it has, it's a bag, then the Fourier transform is analytic, and we've measured it on an open set. So actually the uniqueness problem is simply analytic continuation. You know, if you knew on an open set, you know all its derivatives, you know its Taylor series, and that shows you exactly how it would work, that the solution is unique in this limiting case, but extremely unstable like analytic continuation, and the bigger the open set, the more stable it is. Right? So it has a limited unique solution. Okay, so that suggests how it should go, and it's quite typical of limited data tomography problems. One more slide. Scatter. We model the scatter by using a Monte Carlo simulation. We used a particle physicist code called GM4, and it turned out that our fears about scattering were unfounded. If you put a big container of water in it, like a kind of water cooler bottle, then there would be too much scattering. But you can't get that much water in a bag because it would be too heavy, right? So you can't get enough scattering to really be a problem. And so it wouldn't be that good for people scanning, because people are basically big bags of water. So in this configuration, it wouldn't be so good without a scatter correction. Well, we do have a scatter correction that we derived from our model, but it's perfectly good for things as dense as a bag. And that's all I want to see. Got some references which you can look in the PDF. Thank you.
Miraculum, there is time for questions.
I have a question about the rebinning. As far as I understand, you first do the rebinning and then you do the inversion. Is that correct?
Yeah. So there are 3 steps really. So there's the rebinning to a 2-dimensional data set on the plane, a conventional filtered back projection reconstruction on each plane, which they already have fast hardware to do. And then in our case, unlike normal surface rebinning, we have to separate the answer that's on 2 separate sheets of the surface. So each voxel goes through the upward surface and later goes through the downward surface. So we have simultaneous equations, but in the ideal case, only couples 2 voxels. Of course, we smooth it a bit and regularize it, but it's still very sparse. So you have to solve a sparse linear system.
I understand. So the question is actually, of course, you make an error in doing that rebinning. How do you take that into account, or
because we have error estimates, and remember the cartoons here are very, very exaggerated because the cone angle's very tiny. So the errors that it makes are commensurate with other errors in the system. So we get away with it. But you know, in a way, that's a design criteria. It's not too bad an offset geometry. So.
You indicated that an important part of the technicalities was to solve a system of linear equations by conjugate gradient.
Yeah.
Is that right?
Yeah.
Not just conjugate gradient minimizer, but
Conjugate gradient least squares.
have you got a preconditioner in there?
Well, we regularise it. So we didn't precondition, but we have an ill-post system, and then we're solving a least squares system augmented by a regularisation term. And so the condition number of that matrix is quite good. So CGLS converges very quickly.
But you're not using a preconditioner?
No.
I just thought if you precondition it, you might get the extra bit of speed that you like.
Yeah, but it's of course, if you're trying to implement it on some exotic hardware like a GPU, you also need to make it simple in terms of memory use. So the trade-offs.
So we should go on.
We've got.
Next speaker will be Tron Parslet, and